maybe I can say a few words. We don't know each other, but so we have the pleasure to have Shirley Ho today with us for this seminar. So your group leader meeting at the group leader at for the cosmology and data science group at the Flatiron in New York City. Well, if you want to say a few words about your institute or introduce yourself.
I mean, do you guys know much about the Flatiron Institute? Not yet, a little bit maybe. So it is part of Simons Foundation, and we were funded, I think, by Jim Simons about 4 years ago, when he decided that it is interesting to do computational astrophysics, and he recruited a number of us actually. I was in a group that actually pitched ideas to him, and he accepted it. And the idea is to develop and apply modern computational tools and statistical tools and mathematical tools onto various astrophysical challenges. And so that was the idea of Computational Astrophysics Center here. There are 4 other centers. There's Center for Computational Biology, Center for Computational Quantum Systems, Center for Computational Mathematics, Center for Computational Neuroscience. So they're all like, I think they see opportunities in certain areas when you apply computational tools there, computational and mathematical modeling tools. I mean, it's pretty broad definition what that means. And people in this CCA has a lot of expertise in either sort of the simulation world, developing really advanced simulations of whatever systems they're studying, and also analysis world. So we kind of have both sides. And I see that a lot of our work, you'll see it's coming from sort of both sides of the world and kind of combining them too sometimes. And before I moved to CCA, I was at Berkeley, Lawrence Berkeley Lab. And then before that, I was at Carnegie Mellon, tenure faculty there. And before that, I was at Berkeley postdoc, and I was at Princeton. Before that, I was Princeton PhD. So, and then Berkeley undergrad. So I only go between the coast apparently, except the Carnegie Mellon part.
And you're doing cosmology with different instruments like preparing the Euclid and LSST. And if I understood correctly, today you're going to talk about the interpretation in terms of physics of the outcomes of neural networks, which is a very interesting topic.
Yeah, it's very different. It's not very similar to anything I've done before. So I hope this could be very exciting for all of us, because I'm learning too along the way. So this work is showing work by my students at Princeton, Miles Kramer. Also, Ryu Su at Princeton, who is just graduating. Pavel Lemos from University of Sussex, and now Jeffrey, who is at ENS. Peter Battaglia from DeepMind, Alfredo Sanchez from DeepMind, there's Virgo at Flatiron, who's the Flatiron CCA director and will become the Simons Foundation president, actually, and Kyle Kramer from NYU. I've borrowed quite liberally from a collaborator, Peter Battaglia from DeepMind. So the idea is that how do you interpret a deep network that you usually use, and how do you create an actual equation, analytical equation from this deep network? And here I actually make the problem a little simpler, because you cannot necessarily take like a neural net with like millions or even billions of ways if you're using transformers and interpret it. Not yet, at least. So what we have realized is that you can apply very strong inductive bias, and I'll talk about what those are, and do that, combining with something called symbolic regression. So let me start, and I'll introduce what these very strong inductive biases are and why they're useful. If you have any questions, feel free to really just raise your hands or whatever. I might not see everybody, so you might have to maybe put on the chat so that David would let us know if there are questions, because I will not be able to see everybody, unfortunately, on my little screen on the side. Okay. All right, I'll go without the mouse and see what happens. So how do you understand a scene? I'm going to start from a very physical, but not yet too physical direction. You can actually look at this in a very linguistic way, or physical, or your neuroscience way. So if you look at a scene like this, we tend to parse it into physical objects and relationships, right? So we have, this is very often the situation with pandemic parents. I don't know if people notice this, like things are just messy. And then we have the ground supporting the shell. The shells might be falling off, or maybe the box of toys falling off. Is it attached? Does it fall and hit the guitar? And the floor supports all these things that actually touch the ground. So we try to reason about the objects and their interactions, and we use the word like precarious to describe the situation. And a lot of the situations everyday life, we have this human physical intuition going on, that we look at a system and say, okay, what's going to happen? And it's very similar in physical world. It's very similar to actually everyday, you know, even for non-scientists who parse the world. I know this sounds weird, but non-scientists also have the same sort of physics engine, I think, in the head, where you take an input of a bunch of blocks, you run a simulation in your head and try to figure out what's going to happen next. Same thing for driving or biking, you know, or scootering, all that stuff. You're kind of expecting what's happening. You're predicting what directions things will happen. Would certain actions happen? Would these blocks fall, for example? If these blocks do fall, which direction it's going to go to? So here are some experiments that I would like to show you. So these are the blocks that I was just talking about. And some of the experiments that my collaborator has run is to try and figure out whether it will fall. And it will ask both the humans and the neural engines in this case to decide whether it's going to fall. And they actually had modeled these blocks with something called graph neural net, which I'll describe why it is interesting to look at it this way. Which direction is going to fall, for example. We're also going to make, these collaborators, Peter Battaglia in particular, and his group has been looking into how to reason about a bunch of objects, in this case, other blocks, different masses. How does it affect basically what happens? And here's much more complex scenes. Let me pause some of these other ones. Keeps looping apparently. The complex scenes, it says, okay, would the red or the yellow blocks fall the most? Or, you know, which direction is going to fall? We want to make all these predictions. We can infer the masses. So this is starting to be interesting for inferring masses for those who are scientists, because if you observe a bunch of actions of a system, and you can infer some of the unknowns, which we always like to do, about the system. And here they were actually doing, Jess Hamrick was also within Peter's team, basically infer what masses were in each of these blocks by looking at these animated simulations. You can also predict where all these fluid goes, where when the water comes down, does it go more to the left or more to the right? So there's all these possibilities that are not as, how should I say, as non-commonplace as we would think. These are actually very common scenarios that we play with every day. And scientists tend to do that. Something that I'm going to bring even closer to the astrophysicist here is that, you know, at time t equal to 0, we actually, we want to know what happens. And then time t equals to 1, you know, like the next time step, where is it going to be, and how from time t0 to go to time t1, basically. And by observing this system, can you figure out the rules that govern them? So this is supposedly the Isaac Newton's manners apple tree, the famed apple tree. Whether he did get hit by an apple, we don't know. So how do we go from observing a bunch of things moving around to F equals to, say, n1 m2 over r squared, one of the physical laws that we are very familiar with, the first physical laws a lot of us would learn. We observe the planets moving around and the moons. Can we figure out the physical laws that govern the motion of the planets? We can either work really hard or maybe really lucky, or both. They came up with it like what Newton had done. Or we're going to try to do something called symbolic regression today. And for those who want like a long introduction, symbolic regression is something that relates to genetic programming and evolutionary programming. So it's a really long history of that. For those who just want a sort of layman explanation, I will start in the next slides. What is symbolic regression? We basically have a bunch of mathematical functions and variables. We will form some new equations, and we will check whether these new equations fit the observables. And then you move on to the next new equation to find better fit. The hard part here is to find the next equation efficiently, so you're not basically just doing a full search. So there is a long history of how to do that much better. They like to use the words like mutation, where we swap in and out certain mathematical functions. And what do you choose to be the next mathematical functions to swap in when you do this search of equations is a very, it's a search question, basically. So the possible issue here is that it's a really, really large space to search for the right equation. So what we're going to do today is going to do something called, we're going to use something called graph neural nets to help predict the dynamics first. So for the crowd here, you're like, okay, but we want to do deep neural nets, like maybe a residual neural net. So I mentioned earlier, we want very strong inductive biases. So inductive biases are basically assumptions or prior knowledge that you have about the system that will help you inform the choices of your architecture. Okay, so when you build an architecture, you want to predict these guys moving around. I'm not sure we want to run a simple convolution neural net or residual neural net if what you want is to input are the positions and velocities of these planets at time t1. And then I wanted the same thing at time t2, t3, t4, and then to infinite. So a lot of the analysis earlier that I showed is that you might want to consider how to parse things into objects. And I guess I'm preaching to the choir. Everyone will feel like, okay, using graph network makes a lot of sense because these things are interacting with each other. So the edges are telling you the connections between all these planets. And the planets themselves have fairly sort of simple attributes. Attributes are these properties. So it's masses, or it can be its velocities at that time. It could be some other things. And you can model many things with graph network, but it is much more obvious architecture to use to model these using graph network. And once you model these, we're going to take the graph net. Here's the important part that is new to this work. It's that you take the graph net. If you don't want to listen to anything this talk, this is the part to understand. You take a graph net and you can plug out certain parts of the graph network. For example, I want to understand what the edges are doing. What are they learning? I take that part out and I can use symbolic regression package here that we developed to interpret it. And you can also do the same thing with the node function. So the node function can be, say, summing over all the forces from all the edges and connect all of them, summing over all of them, and then maybe divide by the mass before you can get the right either velocity or like accelerations or anything that you want to work with in terms of the coordinates within each of the node functions. So important part is it doesn't have to be a graph network for what we described to work, but it has to be a network that you can have very sparse representation that you can possibly pluck out from the network and then interpret it. If you give me a billion numbers, this method is not going to work. So if you have a billion latent parameters, you want to sparsify as much as possible. So I'm going to go into some details. That's like the main part of the talk. But I'm going to describe a little bit more of the details. Let me pause here a little bit for questions. People have questions? Sorry, you can hear about New York City. I'm on like 5th Avenue, so you'll hear like lots of sirens and stuff too sometimes.
It's okay.
Feel free to ask questions. I think it's much better we discuss because Zoom talks can get really, really annoying after the first 10 minutes. People are really polite in France. I forgot. So my husband is French, so I sometimes forget how polite they are at seminars. All right.
So maybe one question. Hi, I'm Cyril from Paris Observatoire. So what you vary here is the algebra, say. So you have numbers that relate to some concepts like mass, distances. So these things are set. You don't know what the mass is.
No.
But you know how it's related to a measurement, for example, or you don't know anything about mass, like.
So here so there are two parts of the talk. The first part of the talk, I don't deal with actual data set. This is just a simulation. The second part of the talk, we actually took a real data set from NASA where we had looked at orbits of all the moons and planets for about 31 bodies over 33 years. And for 30 minutes time step. So they actually had observed all this, right? And used that data, just the orbits data, to derive both the masses and the laws. So that was the second part of the talk. But the first part here, which I'm just showing these like little planets moving around, we do not know the masses and we do not, well, we do observe it as velocity and time. So you see the simulation going on, and you can measure its position basically, and time. So you can measure the velocity by default, but it's really just positions and time.
But but you know for example, do you know the dimensions of the in terms of units of these
No.
values?
No.
Scales?
Now, if you know the dimensions, it makes things a whole lot easier.
Okay.
Yeah, there is. This is a really good question, because when we did the second part of the talk, which I will show you, you realize you actually would be getting the relative masses up to a certain constant. So you don't get the absolute masses, because you can always scale things around because of the constants. All right. Any other questions? This is a great question.
I have another question. So you have attributes to each object, but you also have relations between the objects.
And what was the second?
You have relations between the objects.
Yeah, you also have the relation of the object described by these edges. We'll talk a little bit more about this.
What do you call what do you call relation? What is it?
We don't know what it is, because that's what the network will learn. So the network will find a bunch of numbers that basically said there is some connection, there's some relations between these two objects, and we describe it by an edge function. And this edge function will be something that network will learn by looking at these movies or data. I'll describe this a little bit more, because that's definitely, we'll go into graph network in a little bit more details. All right, so now we like to do this in 2 steps. I'm going to explain this again. So simple particles moving around. We predicted dynamics using graph neural net, which we'll describe a little bit more. We also need to encourage low dimensionality representation in the stuff we want to learn before we can feed it into the symbolic equation. Okay. And next day. So let's concentrate on predict dynamics first. And neural net is great at doing this. And we're going to use the graph network, because what we just talked about earlier, that it is much more realistic or physical choice given our system. So back out from the planet side a little bit, a graph here is a natural way to represent the entities and the relations. So like the box here and the blocks before, and the shells with the guitar and everything, right? So nodes here can correspond to entities, objects, or even events. The edges correspond to the relations, interactions, transitions, but we don't know what they are usually. And we'll infer about the entities and the relations, because this is what the network will learn as it observes the data. And it will respect the graphical structure the whole time, which you actually set up. So the graphs can capture many different complex object and relation systems. Could be the molecule like H2O here. The mass spring system is interesting, because you actually would say the spring is represented by a bunch of different nodes and connected by edges. The n-body system we saw earlier could be a fully connected graph with all the nodes talking to each other, because you choose that. I think you assume that they might have connections, and if you don't know whether they have connection, you just let it be connected basically. If you know for sure that something very far away is not going to affect anything here, then you can choose to not have a connection, a connected graph from one point to another. The rigid body system here, the wall is treated as a node, for example, and you can even parse sentences into a parse trees with graph network. And you can also use it to sort of parse a scene graph. But I would say that, if you're going to do a scene like this, you probably want to do convolution or, residual neural net type stuff. So here we concentrate on a particular type of graph network called interaction network. They're all very similar, all the graph network, honestly. They're not hugely different, the ideas. So I'm actually going to exit here so I can use my mouse a little bit better. So here's the graph network. The nodes are the V's here, Vi's prime. So there's all the V's here. The edge is E's, this E of K's. And U is this global property. It could be like the total energy, total angular momentum, the temperature of a system, anything that you can think of that is global. And for the edge function here, let me just describe a little bit. So the edge function right here is described by, there's some edge properties. We can define what these edge properties are. And you will have the receiving nodes. and the sending node. So R being receiving, S being sending nodes. So the receiving, this is sending nodes. It can also be bidirectional. It can be both direction or one direction. And also include the global properties U right here. And you want to compute the message from the node and the attributes associated with an edge. So you want to compute this message because this is something that you learn from watching basically these data moving. And you say, okay, I'm going to learn what this edge is supposed to do. And then you have a node function, which is V here, which would take in all these edge functions, which could be imagining the system we saw before with the multi-body, planetary body interactions. It could be all the forces adding up. It could also be molecular interactions or, between different atoms. I actually, during COVID early on last year, I started modeling COVID rates between different cities, big cities in the US, with different nodes being the cities and the edges being like, are people moving around, stuff like that. And you can have a global rates where, it could be people coming into the country, or it could be, masking mandates and all that stuff. So it was interesting to can model both events and planet bodies differently according to these particular, situation. You can do many things basically. And then you update the node info from the previous node state. For the physicists here, it's not surprising. You'll be like, okay, you sum over all the forces, and then you probably divide by the mass, but also remember you don't know the mass. And you find acceleration x, and you update the node for the next step. And you train to predict node states from T0 to T1. All right, then maybe I don't need the mouse so much more. And here is something for people who are doing a lot of machine learning, given I know this is a very machine learning heavy group. I'll mention how graph network is connected, all these other things you probably have heard of before. For the scientists, very often you probably heard of DeepSet, where you can model a cloud of data points. And you can also do graph network, just remove everything, below the V line, and you'll be very similar. And you can do a relation network, and there's many connections between graph network, even with transformers for those who are doing NLP models. All right. Let me pause here for a question. Any questions here? Because I just gave you a lot of ML stuff and a lot of other ideas. And more importantly, I think you need to understand this part. Questions?
Question, please.
Please. Yeah, there's someone raising hands. David, do you want to moderate questions? Or Philip, sorry, whoever.
Yeah, I can do that. So Rodrigo, go ahead. Yes,
thank you. So you have the node objects, and I was just wondering what the relationships between them. I mean, practically, how are these computed?
You mean, what do you mean? How do these relationships get computed or get decided? Is that the question?
Yeah, no, I was just actually wondering what sort of architectures you use in order to make the
It's a bunch of MLPs. It's a bunch of multi-layer perceptrons. For the very simple idea stuff I'll show you is super simple. The stuff I will show you, you actually can just use a bunch of multi-layer perceptrons. You sum over all the multi-layer perceptrons. For the ML people here, you probably heard of multi-layer perceptrons. And then you do another multi-layer perceptron for each of those decisions.
Right, okay.
It's very simple, right? I mean, it sounds crazy, but it's really just MLPs.
Thanks.
I see hands.
Yeah, Norma, one question.
Hello, thank you.
Hi.
Yes. Hello, Shirley. Yes, and it's connected with this slide and with the previous one, I mean, the 10 minutes, the first 10 minutes of your talks. Perhaps I don't see here which are the data and which are the unknown or the the unknown. I mean the input and the output in some sense.
Let me describe.
Even if that could be very large. And in connection with that, perhaps, I mean, which is your definition of a state here? Which is an state?
Great questions.
Which
Great
is
question.
an state here? Thank you.
Let me start with the input and the output here. So actually, let's go back a tiny bit here. So the input is a bunch of simulations or trajectories of the particles, okay? The output, in our case, is a physical law and the predictions of what happened to the next time step for all the particles. So that's the first question. I hope that I didn't confuse everybody. And I was describing sort of the network architecture within that we use to model, which is the graph network. And I love the question because I like to describe it with all these extra terms, but really you can just do it with a bunch of MLPs. And then is there another question? Oh, the state of the particles here is really the state of the nodes. So it is a really easy data set for us here because the particles' positions and velocities are, and the masses are basically what we care about. And these are the states and the attributes, you know. Does that help?
It's very simple state. I mean, very simple.
Very simple data.
But excuse me, just very, very briefly. But please. You have, I understand, of course, that, but you have some parameters. I mean, you have unknown parameters or free parameters in the in your, I mean, for instance, extract to symbolic equation. There you have you have the, I mean, you extract the equation or the law set in general, but inside you have parameters to determine. These parameters are not all known.
Yeah, so there's a
for
really
instance, the masses or the sizes or other attributes of the spins, if you want, I mean, or angular momentum.
This is great question. This is all great questions. There are parameters everywhere that you can tune. And, you know, for those who do machine learning, you definitely use a set to basically tune all these parameters. But let me describe the parameters separately from both the architecture and that we use in the graph network and also the symbolic regression part. For the symbolic regression part, the most important tuning that you will need to do and that actually affect things are the fact that you will find a bunch of equations and they're of different complexity. And the more complex, basically the more parameters you throw at it, the more accurate usually the output will be. But more accurate doesn't mean that it's the correct law. You want one that is correct when you generalize to a situation you weren't trained on. So there is something called the Occam-Razor rule, where you have to decide how much you value the simplicity and generalizability of the equation that you find, and how much do you want it to be very, very accurate, because you can have like a crazy function that have everything accurate for the training set, but it might not generalize well. So the symbolic equation part, the most important parameter that you need to sort of figure out is which equation and how would you tune which equation you should pick up. And what you do is that you plot the error of the equation versus complexity. And usually it is, you know, dropping error as you increase complexity. So when you go, sorry, the direction is probably difficult to show, but as you go to the right-hand side with increased complexity, you're gonna have dropping errors on the prediction of the equation, like how well it's doing compared to the data. And then you will see a steep drop where you realize that that is enough complexity to describe the situation, but you don't want to keep increasing the complexity when you have low enough, basically, error bars. So that's I think the most major thing that we find out is to realize you need to take that big drop as indicative of, you know, the equation is found. It's very interesting, this part. And then for the graph neural net part, there is definitely some parameters to tune, but there's not as many as you would think. And you'll see the network very soon, and it was very simple, actually. Let me show you. Before I go on, is there any questions? I saw someone talking before. Or did I answer all the questions already accidentally? All right, we'll start going. So here is the planetary interactions. So here is the input. Each planet is a node X, Y, M. It's just as a function of time. For any pair of planets, there's an edge, and there's just a fully connected graph. Each edge is a function of 2 nodes. The update on each node would depend on all the edges, which in this case forces acted upon it. And here is sort of the architecture, really. It's not so complex. It's a super, super simple network at some point when you think about it. You have the graph network, and I like to show the analogy to Newtonian mechanics for the scientists here because it makes it so much easier to understand. The nodes are the particles, and then their pair of nodes are these 2 interacting particles. And the edge model here and the node model, these black boxes, are the neural network. And we actually just use multi-layer perceptron. You can do other things too. And then for the edge model, you compute the force because we think it's the forces that actually matter between the interacting particles, but the network doesn't know. This is just an analogy that we had in the back of our head, but that doesn't mean that the network knows what's going on. And you pool, which means you sum over all the messages together. You concatenate all this stuff with the node to the node model, which means at some point you have to calculate the acceleration of the node to update the next time step. And you update the nodes, you compute the next time step. And once you realized what's important here is to encourage something called sparsity. I see you guys, I can't use the mouse, unfortunately. When you compute all these edge models and node models, you want to encourage sparsity so that you don't end up with a million parameters. You want to end up with maybe 10 or 20, mostly because of the fact that the symbolic regression doesn't really scale well yet with large number of inputs. Like if I tell you there is like 20 different numbers at 20 different quantities that might be affecting certain situation, it's very hard to find the right physical law because it's just going to blow up the search. Outcome here is the truth versus the model. The training was done on 1 step every time. So there's a lot of training sets, but what it's learning is 1 step, and it keeps rolling out for 1,000 steps in the future. So you see that is the rollout that I'm showing right now for 1,000 steps in the future, and you can see they're actually very, very nicely done. Not everything is so easy to model, and you can see this is the 1,000 step rollout on the top, which is the true versus the predicted in the bottom, what you can actually see. When you say 1,000 step rollout, is that you do not actually have the training set showing you anything for 1,000 steps forward that way. You just predict 1,000 steps forward and let the system, tell you what should happen next. The hardest one is surprising. It's actually not so surprising when in retrospect, is that these balls in the wall is much more chaotic and it's very difficult to predict. While the n-body systems much easier to roll out very nicely. The spring mass system is also pretty simple to predict, which is pretty good. And there's this zero-shot generalization to larger system, which I think it's very interesting. What is zero shot? For those who don't know about zero shot, means you never seen a data set. You never train this network with anything that has this number of body or this number of balls or this length of mass, the springs or the masses. So, but you've seen different systems before. For example, you have seen this one with smaller number of, planetary bodies, but you have not seen something with that many number of bodies. But it still works okay. It's not perfect, but the fact that the network has learned something physical enough to still model moderately okay, given that it's rolling out 1,000 steps in the future, I think it was pretty interesting. And not to mention that there is intrinsic chaos in the system. Even when you simulate it, if you make a slight error, well, not even slight error, machine precision error, that you can still see the divergence behaviors for some of these quite quickly. So this part, we now hopefully have convinced you that we're able to make predictions, compare with the data and update the weights, and all that has made the network able to predict what happened in the future, at least more or less correct, especially for the n-body systems. It's doing quite well. The balls bouncing in the box is much harder because the chaotic behavior comes in way earlier. So now we have this big challenge, how to extract the equation. So here is sort of nitty-gritty details. I'm not going to go into all of them, but the main thing to realize is that you have a bunch of latent parameters, and you don't want all of these to be fed into this symbolic regression search. Instead, you want to make sure it's as sparse as possible. So we apply something called L1 regularization to reduce the number of latent parameters that the network, well, not the network, actually symbolic regression will have to fit later on to extract the unknown force. Why do we use L1 regularization for those who are, experts in this field? We tried a bunch of different ones, and this is the one that worked the best for this system. Here it also responds to the questions like, are the parameters you're tuning? Yes. How do you make these latent factors as basically sparse as possible? So we also know that when you train for a certain system, if it's 2D, you probably don't need so many parameters, not 200. When it's 3D, then you should only have maybe 3. So when we try to actually input and say, okay, if it's 2D data set, you only use 2 parameters, that doesn't work very well. We actually end up using L1 regularization was better. So this is describing how our thought process went through actually. When the input simulation is only 2D, we do not expect the dimension of the edge factor to be larger than 2. But then when we find that, limiting it to exactly 2 immediately makes training much longer and the performance not so good. We instead try a bunch of different regularization techniques to lower the number of, latent parameters that we need to fit. And L1 regularization turned out to be better. We actually had new work that's on this area that I can talk about it later, that how do you actually sparsify a latent factor is actually quite important. And then we put the edge element through the symbolic regression and see what would fit for the 2 elements. And we can see that it's basically a rotation of the true force, which is really kind of cool. So we recover the force laws from observed system, including the springs mass system in 2D and 1/r² law in 3D, which we were pretty surprised about. So people were asking us, why do we do something so easy? So we decided to do something harder because they said, well, you already knew these laws to start with. So can you do something a little bit harder that we do not know the answer ahead of time? Also to avoid us tuning any parameters to get at the right answer, right? So here's what we decided to do. We take a dark matter simulations. For the cosmologists here, this might feel a little bit more familiar. This is actually illustrative simulations. It's showing the gas temperature right now. And I'm just showing a part of the simulation. That's probably an explosion of supernova. And as we move forward, you will see that these gets really complex if they're nonlinear. And you know that will form dark matter halos. That is basically the structure hosts most of the galaxies in the universe. And the blue dot here really follows the dark matter filaments of the cosmic web. So all this stuff is, things we know and care a lot about. And what we want to ask ourselves, something we never really knew the answer from before. So what is the density of dark matter within the center of a dark matter halo, which is sort of the cluster of galaxies for those who don't do cosmology, given the surrounding halo characteristics? So just remind me, let me remind you again, a bunch of halos around the central halo. Can we get the density of dark matter within the center of the dark matter halo in the middle? We can make guesses of what this answer may be like, but we do not know a priori what this analytical formula is from previous work, because we just don't know. You also wonder why people never try to predict this too. So we took detailed dark matter simulations of full n-body simulations, dark matter. We try to predict the properties of these dark matter halos, and we take all these neighboring dark matter halos and try to predict what's the dark matter density in the center of the central halo. And we basically would say, okay, what is this dark matter overdensity equation that we never really looked into, and not just we, but just in general the cosmology community. So we did all that similar things, do the whole thing like before. We model the dark matter halos as if they were basically the graph network using that particular infrastructure. And then we use symbolic regression to extract a known equation. So that's what we got here. We actually found a new analytical formula that fit to the observable in at least these simulations better than what we can fit for using just physical intuition. So when I say old, it's basically what we can come up with very quickly. Here shows the test, the formula we came up with or the network came up with, and the sum components, what these things are, like the EIs, and basically the MSE at the end. So the lower, the better in terms of error at the last column on the right. And you can see that for our intuition, try to constant, try something very simple, the simple test one. That makes sense, right? So you basically have a constant, you have some constant, it depends on the mass of the central halo, probably depends on the surrounding halos masses and all that. And we realized that the best formula that the network came up with is, first of all, different from our simple analytical expression that we came up with and performs better. And so far, we're just trying to figure out why this formula makes sense. And you can also tell the network to say, okay, let's say we don't know the mass of these halos. We only get, say, the velocities from the spectra. And then you get a different formula because all you get is just the velocity of the spectra, for example. And I thought this is a pretty interesting situation because now we have a new formula describing the central density of a dark matter halo according to its neighbor dark matter halos that we don't know what this equation is telling us because we haven't quite seen this before. And it's performing better in terms of predicting what the central dark matter halo density should be. How about using some crazy real data? So I'm going to quickly go through this because this is nearly exactly the same as the planetary data that we had before, except this time we use real data. We took orbits for 30 years and they in 30 minutes time slots in terms of like the data from NASA Horizons Ephemeris System data. And you also took the moons, not just the planets. There are about 31 bodies that we end up picking above a certain mass thresholds. And then we used these actual orbits to do exactly what we described before, which is kind of cool. The graph network was used again. So GN here is the graph network to describe all these planetary systems, these planets and all the moons. We sum over all the forces acting on each body and divide by the nodes to get accelerations. The loss function is obtained by comparing this sort of predicted acceleration to the true acceleration. So that's when you learn by looking at the data. And then we left 3 years of data without using it for training and see whether the graph network has learned for testing. And it has actually learned really well, as I'll show you later, right here. So here is the data on the left from the inner solar system. And here is the learned bodies evolved from the same initial conditions using the learned interactions without all the other orbits. This is just taking the learned interactions and evolving it forward, which I think was pretty cool. And even better, we get the masses. So, in terms of solar masses, so MT is true, MP is the predicted. And you realize some of these we don't do very well, right? So the learned scale is relative to the sun, because the ones that are really small masses compared to the mass that is actually going around. So some of the moons are very, very light compared to the planets that's going around. We actually don't do very well, which is actually a good proof that you should have an error, given the interactions are very small compared to the big motions. Also, for the planetary system, the heavier planets will actually do better in terms of, because it's actually basically the planets with the sun for the planetary system within our solar system. And you realize that Jupiter is doing the best, and like the heavier ones are doing better, and Venus, Mercury not doing so well because they're really light. So I hope that, and Saturn is also spot on because it's so much heavier. So conclusion here, I know it's coming late. We have human intuitions, physical intuitions to help us create new ways of thinking how to do machine learning. these new ways of doing machine learning, such as graph neural net, help us simulate what we see in the real world, I think, faster. And what is more intriguing is that even for physical laws that we don't know answer to, like the one about dark matter density, we can sort of observe the system and let ML help us find the analytical expression. And I'll add to the point that we can actually use real data to basically do an actual understanding of the system, finding a physical law and also deriving unknowns from observing it, without actually deriving Newton's law with some genius from before. Thank you. I'll take questions from here.
Thank you so much. Françoise.
Yes, thank you. It was very interesting. I was stricken by the fact that normally in machine learning, you need a lot of objects, a lot of data and so on, millions of data. And for this, maybe it's better to have a fewer data, no? Because if you have only...
We don't need that much data, not necessarily. I think
to recognize a cat or a dog, in fact, you need a lot. And people were always telling us that it did not work when you had not enough data, now it works. But for the laws, it's much better to have less, because if you have two planets, you look their motion during several years and you know the laws, while when you have 10 or 20, it's not better.
That's absolutely right. I think there's a lot of prior that we applied at some level because of the inductive bias I talked about earlier, that you knew what this system is sort of about, not exactly, but the fact that you saw, two bodies moving around, you know that the interactions is just between the two bodies. It's not there's some outside forces. It's not recognizing cats and dogs, because cats and dogs, there's no structure in it. There's no physical rules to it. And these physical intuitions really helped us. And so we actually don't need that much data. These are very small amount of data compared to what people talked about all the time. And just to give you a sense, a lot of our work, we done some work to map from dark matter to galaxy and say, if I have a dark matter distributions, can I map to galaxy distribution? And we only had one training set, which is the Illustra simulation, or like maybe two. And we don't need a million of them. So I don't let anyone tell you that, oh, you need a million training sets, so it's not possible to do it. A lot of it depends on what prior, and prior is really just what they say, inductive bias in some level, like what prior you have about the system and how much you can make the network know what you know without biasing it. So I think that's a little dance that you have to make sure.
Mm-hmm. So in fact, we can distinguish several problems. Once it's for classification of images, like galaxies. When you want to classify galaxies, you need a lot. You don't have enough with 10 or 20, but you need the millions of galaxies to better classify them. But for the laws, the fewer, the better.
I'm not sure it's necessarily fewer, but I think the role of inductive bias is stronger in laws and in also physical systems. But images of galaxies, if it's just from an image, it's not as obvious what the structure is. But I think there is an interesting work probably people can do is to look at how many latent parameters do you need to model an image of a galaxy. I don't think it's as many as maybe even cats and dogs and animals, because there are not that many types of galaxies. I mean, we know the sequence.
More than cats and dogs, I would say.
I don't know. There's so many types of cats and dogs.
There are several pixels, more pixels than that.
I don't know. But yeah, I mean, we have some interesting discussion just yesterday about whether we can find some rules. I wouldn't say physical law, but rules about even classifying faces, because there's a structure on faces. But if it's like a random image on the web, then it's unclear. Or even fashion amnest, for those who were thinking, these clothes have structure. So that's a different discussion. That's not cosmology or astrophysics.
Thank you.
I have a question about the edge functions that you, if I understand correctly, so the reduction of the edge function will lead to what could be the law. But then it means that the way you define those H function, it defines kind of a language from which you can extract or not the law. So it's not clear to me how you define those H functions. I mean, is it completely free, or is it like, I mean, do you put polynomials, exponentials, or do you use mathematical functions or to derive those laws, or?
You let the symbolic regression pick it, actually. So we don't say you should use exponential or polynomials. You should actually, the network just this, I mean, the symbolic regression package decides it. It's a big search. That's why you don't want too many of them going into the symbolic regression part. By the way, the best part about this talk is that everything is public. Let me just send you guys this. Can you still see my screen or no?
No.
Okay, let me show you. Hold on a second. So and everything is public, and we have even notebook ready to go, and code, and even simulated data. So I think it's actually excellent for those who want to play, and it's really easy. You can just run it on your, if you have a Google Colab, you can literally just run it. If you, this is a Twitter link, but the Twitter link has the blog post, the code, and the paper. And here's a very simple description of how it worked, because it's Twitter, so you don't have that many characters. I see other hands raised. David, do you wanna, Philip, do you wanna?
Yes, Rodrigo, please go ahead.
Yeah, thank you very much. That was really awesome. I very much enjoyed your talk. So I'm still a bit unclear though as to how the symbolic regression part works. Do you then make predictions that you go back and sort of feed back into and compare to the original data? Is that done at all, or is it purely deducing the laws from the edges that as was?
Yeah, so this is a great question. So this is actually something someone asked me like a few days ago too. So the network, the graphical network, is trained before the symbolic regression actually is called. So, right. But then the graphical network, when it's training, the important part is that you need to sparsify those latent space, because you want to have as few parameters we need to actually understand as possible. So that's what L1 regularization I was talking about. But that network is doing all the comparisons with the data during training. The symbolic regression doesn't do any training at all. It doesn't see the data actually, except for those latent parameter expressions. This is a great question. These two are separately done. We actually are hoping to try to combine those two as much as possible in some ways, because both of them are doing some kind of gradient descent when you think about it, because the graph network is doing some gradient descent to say fit to the data that is trained on, while the symbolic regression is doing some basically search on this huge parameter space for equations. And they're doing, well, currently we have it separately doing different gradient descent at some point, right? I call it gradient descent, but they have different ones.
Well, thank you very much. It's awesome. I'm going to go and take a look at this, at your code. Thanks very much.
Yeah, the code is right there, and everything is there, which is really nice. The student had made it completely easy for those who are wondering. There's also interactive notebook, which has all the data, and you can load it. That's the blog post that's actually linked from the Twitter too.
Yes.
Norma?
Yes, thanks again, Shirley. I have 2 or 3 points said very briefly. First, perhaps, is about your, you found, you said estimation for the dark matter central density, okay? You, with respect to the simple one, you find the one then from the simulations you take. The point is, I am not sure in the formula you show if, because it's a switch in denominator, perhaps there is a misprint in the formula from when you show the simple Formula 1, and then the best you find with this symbolic regression. It seems that there is a misprint in the slide. So I wanted to clarify that point. And connected with that is if you take, of course, another simulation, because there are too many different recipes and ingredients and all kinds of simulations. So you will find another type, or even if relatively similar, but you will find another types. So perhaps with with your, techniques, or these methods, it could be possible to take and comparing and make some set the best or optimization of that. Is what I am trying to see. The other points perhaps are more difficult. Could you find if in the system, whatever you have a dispersion law or dispersive laws, viscosity, for instance, if in this system of many bodies with velocities and all that, besides the interaction, any body and so on, you can find as a law of the force proportional to the velocity. That I think, a viscosity, if there is a viscosity in the system, which you didn't know from the beginning. That I think is interesting because it makes connection between the variables, the nodes you have. And the other is
so Norma, yeah. I'm sorry, I have to cut off quickly just because I'm going to my students' thesis committee meeting, supposedly at 11. But I quickly want to respond to a couple of your questions, which I think are extremely interesting. For the viscosity one, like getting some of the unknowns, we are applying the same idea that we just described here to turbulence simulations right now. And in turbulence simulations, there are viscosity that are numerical, and there's closure terms that we don't know how to describe theoretically. And we actually, we're not published yet, but the first thing we did is that we recover the equation that were in the system, that were actually being simulated. The second thing is that we found numerical viscosity terms that looks like numerical viscosity. We don't know yet. We're still trying to figure out, if these things generalizes, if these things are, truly the correct terms that we expect. This is completely in progress, but I think, yes, you're very right that the exciting part is finding these unknowns. And hopefully for the turbulence projects, we want to find the closure terms, which will be super awesome. So yeah, that's super cool, that what you just described. I forgot what all the other questions, but yes, so checking for different simulations. What we always do is that we train with a set of simulations, and then we check it with different set of simulations, but they are of the same distribution, in the sense that we're not running a different n-body codes with a different resolution and a different everything. So we could do it, which is also going to be interesting, is try to use a different n-body code with different resolution and see whether the formula applies for the dark matter density. Thank you so much for all the questions, but feel free to contact me. I just really need to run to the student. He's texting me on the side.
Thank you very much.
Thank you. Thank you.
Thank you so much for joining. I know it's a tough time. I hope we'll get to see each other soon in person. Thanks
a lot. We'll put your links to close to the video so that people can go to the notebooks or download
those notebooks are freely available. I'm not charging anybody, except maybe coffee in Paris. All right, I should go because just the students are like, you have to come.
Bye-bye.
Bye.
Bye-bye. Thank you.
David, Philippe, vous avez